class. In this today's video, we are going to see the applications of colorimetry and spectrophotometry. In my previous video, we have learned the instrumentation part of both of these instruments, how they differ from each other. We'll just recapitulate that part of instrumentation variation with respect to colorimeter and spectrophotometer. The wavelength variation in colorimeter we use visible range, whereas in spectrophotometer we use UV as well as visible range of wavelength. The source utilized in colorimeter is tungsten filament lamp, and in spectrophotometer deuterium lamp. The filter utilized are absorption filter in colorimeter and interference filter in spectrophotometer. The monochromator applied in colorimeter is prism, whereas in spectrophotometer it is diffraction grating. The sample holder utilized in colorimeter is simple glass tube, whereas in spectrophotometer it is rectangular quartz tube. Detector applied in colorimeter are photovoltaic cell or phototube, whereas in spectrophotometer it is photomultiplier tube. Sensitivity is very high. Spectral isolation filter need to be changed in colorimeter, whereas desired wavelength we can achieve in spectrophotometer. The broad band is utilized in colorimeter, whereas narrow band utilized in spectrophotometer. The concentration variation, both of these instruments works based on Beer's law, where absorbance is directly proportional to concentration. Now, the concentration utilized is dilute concentration. In case of colorimeter, we'll go molar concentration, whereas in spectrophotometer, we can decrease the concentration up to ppm level or micrograms per liter. Accuracy is less in case of colorimeter compared to spectrometer. Spectrophotometer cost is definitely low for colorimeter compared to spectrophotometer. Now, looking forward to the application part, we broadly classify the application as qualitative and quantitative application. Qualitative, where very good, what we do in qualitative, we just detect the components, whereas in quantitative we found out concentration of particular component. Now suppose if I gave you a solution which is having more than one color compounds, mixture has been provided to you, and you have scanned that mixture over a spectrogram and obtain a spectra like this using spectrophotometry. Now this dotted line is the spectra obtained to you. Now qualitatively what I can say from this spectra, there are three colored components present in my given compound. This is possible as you are scanning through the whole range UV as well as visible. Absorbance is an additive property. You can add or you can subtract the value of individual component. If you will subtract these two, you will get this peak. If you will subtract this one, you will get the simple. So depending upon the absorbance peak maxima, you can see there are three components present. If you scan a single compound over whole range, you will get the absorption maxima on spectrophotometry. This maxima tells me this is the maximum absorbing wavelength for this particular compound to be utilized. You will get transmittance graph 2. There are different terms utilized in photometry. We have seen this. We just recapitulate these terms. Where radiant power, the source of light we are using, incident beam, that is termed as P0. The amount of light transmitted from the sample is termed as transmittance. T equal to P upon P0 or percent T, we can calculate T multiplied by 100. Absorbance or optical density, it is negative log to the base 10 of transmittance, or A equal to log P0 upon P, or A equal to ABC or KBC, or percent I can calculate by multiplying simply 100. Absorptivity, I can find out absorptivity by rearranging this equation where small a is absorptivity. Small a is absorptivity. You can rearrange the equation, the ratio of absorbance to the product of path length and concentration. Here you need to rearrange this equation. Molar absorptivity, we can find out molar absorptivity by simply multiplying molecular weight with respect to absorptivity to get molar extension coefficient epsilon. The unit of this is liter per mole per centimeter. Here we have not discussed any unit as there it is a ratio. So transmitter's absorbance is unit less quantity. Path length, you need to express path length in terms of centimeter. Now the quantitative application, that means where you are interested in finding out concentration of unknown concentration of colored solution. Now if this is the task given to you where you need to find out concentration of colored solution, the concentration is unknown to you. Now same solute you need to pick up, you need to prepare 4 or 5 known concentration solution of that particular solute, dilute concentrations. The highly colored solution among them, you take that highly colored solution and scan over different filters available on your colorimeter or spectrophotometer. Through this particular task, you'll find out maximum absorbing wavelength. How? The absorbance is maximum at particular wavelength you'll obtain. That wavelength you termed as maximum absorbing wavelength. Or if I scan the colored solution on spectrophotometer, I'll get in this way the spectrogram. This is the highest absorbance at this particular wavelength. So I can say 276 nanometer is lambda max for my given solution. Task 1 is completed. Next you have to do, fix this wavelength constant on your instrument, scan all other dilute solutions at this particular wavelength, you will get absorbance values. You plot those absorbance values on a graph having absorbance versus concentration. You will get straight line passing through origin that obeys Beer's law. Now for unknown concentration solution, you just find out absorbance at the same wavelength. The absorbance value is there with you. You drag that over this graph and you'll get concentration of unknown solution. This is one of the way experimentally to find out concentration. Theoretically, if the sum is given to you, you can simply apply Lambert's-Beer's law, substitute all the values given to you and find out concentration of unknown solution. Suppose two different solutions of same solute are provided to you and they have provided to you for known concentration this data like absorptivity, path length, concentration, absorbance. For second solution where you need to find out unknown concentration, the C2 value is not provided to you but absorbance is provided to you, A2 and B2 is given to you. For same solute, the absorptivity remains same, whereas for same instrument, path length remains same. So A1 upon A2 equal to C1 upon C2, simply utilize this equation to find out concentration of unknown solution. In case of inorganic compounds, coordination compounds, where if we know mole ratio, number of moles of ligand and number of moles of metal, if it is known to you, it is easy to prepare the complex. Now, to know the mole ratio of these coordination compound, we can apply spectrophotometry or colorimetry, where there are two different methods to find out mole ratio, where mole ratio method is there and second is Jobs variation method, where metal to ligand ratio you are varying. We'll see the first method, that is mole ratio method. In this case, you need to have the different moles, you need to prepare a solution where you are putting different moles of metal and ligand. In this method, either of the metal or ligand concentration you need to keep constant. So if you are having 5 or 6 volumetric flasks like this over here, you put metal concentration constant, you do variation with respect to ligand. Now metal and ligand combine and form a colored complex. Now, when exact ratio of mole ratio matches, the colored complex shows highest color intensity. Now, the task of preparation of solution you have done, you just scan those prepared solution over known maximum absorbing wavelength. You find out absorbance of all these prepared solution. You'll get a graph like this. Extrapolate the lines and find out exact mole ratio for your given coordination compound. In second method, they are doing variation with respect to preparation of solution in such a way that addition of metal to ligand, they are doing in such a way the total concentration they are keeping constant, but they are doing variation with respect to amount of metal and ligand added. This pictorial presentation tells me that here one of them is having highest concentration and then concentration decreases. Now if you scan this for maximum absorbing wavelength of this coordination compound, you'll get graph like this, where this is the extrapolating these lines, you will get this is the maximum absorbance, or you can find out mole ratio for the particular compound. Structural variation with respect to organic compound or inorganic metal complexes easily detected by scanning these colored solution over spectrogram, where there is definitely a variation with respect to absorbance in case of the position of the compound, position of the attached groups. For example, I have tried to show over here where the absorbance of trans compound is higher compared to the absorbance of cis. So you can do the variation that observed cis isomer of this particular compound is violet color, whereas trans is in green color. So observation you can correlate by taking or scanning the particular solution over whole spectrogram. Similarly, in case of organic compound, the substitution of group over a benzene ring makes variation. These variation increases the length of resonance. Increase in length of resonance increases the transition of electrons from pi bond or sigma bond, which increases the absorbance. So increase in absorbance you can correlate structurally and find out the structural correlation qualitatively in case of these compounds. Further, qualitative analysis with respect to the organic compounds, where these are, just now we have talked, chromophores are the compound which are chromophores, I can say carbon-carbon, double bond, carbon-carbon, carbonyl linkage, where this sigma and pi bond in these particular groups absorbs the light and shows transition from sigma to sigma star, pi to pi star, or n to pi star. These transitions are responsible for giving the color to the compounds. These colored compounds deepens their color if along with these chromophore oxochromes are present, like OH, NH2, NR2. If I add these groups over the basic structure of organic compound, they show shift in absorption towards longer wavelength. If you observe shift in absorbance towards longer wavelength, that is termed as bathochromic shift. If you change the solvent, you may observe also the shift towards the longer wavelength, that is red shift. If you observe shift towards the lower wavelength due to presence of these groups, due to addition of these groups like OCOCH3, NH3OCO3, then that is termed as blue shift or hypsochromic shift. If absorption intensity increases due to presence of such groups or solvent, change in solvent, if I see that increase in intensity of absorption, then it is termed as hyperchromic shift. If decrease in intensity of absorption, it is termed as hypochromic shift. Similarly, solventochromism. If I measure the absorbance of particular compound in less polar solvent, if I change the solvent to more polar solvent, again shift in absorption observed, termed as positive solventochromism. Shift in absorption to lower wavelength, termed as negative solventochromism. This is is one of the best application of colorimetry and spectrophotometry, where you are analyzing binary mixture with respect to individual concentration of component. Suppose I have given over here blue color and green color, two different solutes mixed and given to you, and task has been given to you to find out concentration of individual species present in a given binary mixture. Once you scan this binary mixture over spectrogram, you will get a spectra where dotted line tells you that this is the spectra where two different components are present. Qualitatively, you can see this is the highest absorbance for the first component at this particular wavelength. So this you can term as maximum absorbing wavelength of this blue color solution, showing highest absorbance. This is the wavelength, maximum absorbing wavelength for the second component. So you can find out the concentration of individual component by performing further steps, like you have to pick up a particular solute, prepare different 4 to 5 solution of this particular blue color solute, where known concentration dilute solutions you need to prepare at the maximum absorbing wavelength of this particular X solute. You need to scan all other solutions which are prepared known concentration. Again, you need to prepare for this green color solute the known concentration of 4 to 5 solution at this maximum absorbing wavelength. You need to scan the green color solution and find out the straight line passing through origin, which obeys Beer's law. The slope of these straight lines gives you the value of molar extinction coefficient of these two components. Second task you need to do is compound Y. You need to scan or find out absorbance at wavelength lambda 1, which is not its absorbing wavelength, so definitely you will get lower values of absorbance. Similarly, compound X is scanned at Y2 wavelength, you will get lower absorbance and you will get the values of molar extinction coefficient, which are with respect to wavelength utilized. These values are useful further to find out individual concentration in given binary mixture. Suppose that binary mixture, if I put at this particular wavelength of first lambda 1, I will get absorbance 1 for mixture, which I can split and write down individually as it is additive property absorbance of x1 component, x component and y component at wavelength 1. Again, I can write down further the molar extinction coefficient and path length. Including these values, I can split my equation for finding out absorbance at wavelength 1, finding out absorbance at wavelength 2. So these two equations are useful further to find out concentration of individual compound. You need to solve these equations simultaneously to find out the values of C1 and C2. P remains constant throughout the experiment, and epsilon values you can calculate from these graphs. A1 and A2 are known to you from these wavelengths, so you need to find out C1 and C2. Solve simultaneously these two equations, you will get final answer C1 equal to epsilon 22 absorbance 1 minus epsilon 21 absorbance 2 divided by epsilon 11 22 minus 21 12. So putting all the values in this equation, you will easily calculate the individual concentration of compound in binary mixture. Next major application is you can perform spectrophotometric titration to find out equivalence point of particular titrant and analyte. Now, to perform such titration, whatever titrant, analyte and product, these three entities we are utilizing, either of them should be color. That is the basic necessity. Now, what you will do during titration, you need to put titrant in analyte, and for every addition, you need to find out absorbance, where absorbance you will find out at a fixed wavelength. So for this particular titration, what is the maximum absorbing wavelength to be utilized? That data should be there with you, or you need to find out by putting known amount of increases, or we can say dilution error of this particular titration we can minimize by taking always titrant 5 times concentrated than analyte. Once you get all absorption values, you need to plot these values on absorbance versus titrant added. You'll get two straight line. Extrapolate these lines to find out the end point. We'll discuss few more cases based on this spectrophotometric titration further. First case where only analyte absorbs. Now what you are taking, titrant is there in the burette, analyte is the solution in conical flask, and product will form in conical flask after addition of titrant. Now here only analyte absorbs means only analyte is colored. So while starting the titration, I'll start measuring the absorbance before addition of titrant, after addition of titrant too. So initially absorbance is high because your analyte is colored, titrant is colorless, product is colorless. So as you add titrant, as the product form, the absorbance decreases. When completion of whole analyte is utilized to form product, the absorbance remains constant. So you'll get nature of plot like this. When only, second case, when only titrant absorbs, that means the solution which is there in the burette is colored. Analyte is colorless, product is colorless. Such type of solutions you might have utilized in simple titration like K-4. Keep in mind in front of you while we are discussing this particular curve, where your titrant is colored, oxalic acid or the solution analyte is colorless, product is colorless. So during this titration MnO2 form is colorless. So when you are titrating, putting K-4 in oxalic acid solution, the product form is colorless. Till your oxalic acid is in existence or product formation completes, excess of addition of K-4 shows increase in absorbance. Extrapolate these lines and find out equivalence point. Next case where only product of titration is colored or absorbs, where initially whatever analyte is colorless, titrant is colorless, product is colored. So when I am putting titrant in my analyte, it will show increase in absorbance till you are forming a product. Once product formation is completed, excess of addition of titrant shows me constant absorbance. So nature of the plot you will get like this. In next case, both analyte and titrant are absorbing. It indicates product is colorless. Analyte is colored. So initially you will get higher absorbance. As the product form, it decreases in absorbance because product is colorless. As completion of reaction is there, excess of addition of titrant which is too colored, then increase in absorbance, or you'll get V-shaped plot. Both the titration reactions, product and titrant absorb. Product form absorbs as well as excess of addition of titrant absorbs. And in next case, where we are studying the reaction of indicator with acidic media as well as basic media to find out pKa value. That also we can find out the degree of dissociation constant for indicator by using spectrophotometric titrations. Looking at the advantages of the spectrophotometric titration, that we don't need to add indicator. We can do the titration very rapid, selective, non-destructive and with high precision. We can perform such titration in aqueous media as well as in non-aqueous media. And if any impurity present, it can't interfere as the reaction takes place between analyte and titrant. These are few references I quoted over here. You go through this, solve many more problems, theoretical problems based on colorimetry and spectrophotometry, utilizing simple basic equations of Beer's law, Lambert's-Beer's law, to make masters in the theoretical problems. Hope you enjoyed this video and understood the applications of spectrophotometry and colorimetry. Thank you. Please like, share and subscribe this video. Thank you.